Hello everyone, it's Dr. C. Quick pre-lecture here on the relationship between the free energy change, the cell potential, and the equilibrium constant. Okay, so recently we looked at the relationship between the free energy change and the equilibrium constant. All right, and so let's start with two equations that you should know. All right, so two equations that we learned. This was a section in chapter 18, I believe, where we related the free energy change and equilibrium. All right, now we've talked about this, but it's always good to review this. The non-standard delta G and the standard delta G tell us slightly different things. So the non-standard conditions, delta G, that's the one that tells us spontaneity. Is the reaction spontaneous in the forward direction? Is it spontaneous in the reverse direction? Negative, forward, positive, reverse in terms of spontaneity. All right. Now, the standard state delta G, standard conditions. Again, standard conditions, pressure of any gases present would be at 1 atmosphere. Any solutions present would be 1 molar. That does not tell us spontaneity. What that tells us is equilibrium position. When that system gets to equilibrium, will the equilibrium lie to the left, toward reactants, or will it lie to the right, toward products? And the sign convention should make sense. Negative, equilibrium lies to the right or to products. Positive, equilibrium lies to the left or toward reactants. Okay, so we've already done this, but it's always good to review this. Okay, now looking at the second equation, note again that it is the standard conditions delta G that is related to the equilibrium position. That is the equilibrium constant K, and hence, you know, if we have a large K, well, let's do our sign convention. If we have a negative delta G standard, okay, that's a G, I apologize, that kind of looks like a 6. Okay, then our K should be large in magnitude. Okay, negative delta G tells us products are favored. If products are favored, we should end up with a large K. Positive delta G standard, we should end up with a small k. Positive delta G standard, reactants are favored at equilibrium, small equilibrium constant. Okay, so good to know. You should know this already, but nice review to start. So then we can now move to cell potential. All right, so we're going to look at 3 more equations. Now, we're not going to derive these. We can kind of make sense of these if we actually look at the units, and we'll write both the standard conditions equation and, oh gosh, I gotta write a little bit more clearly here for you. Okay, so we can write this same equation relating the free energy change and the cell potential at both standard conditions and non-standard conditions. Okay, so we'll work problems in class where we plug in and solve. Just a couple of things to know. F is named after Michael Faraday. He was a scientist that did a lot of electrochemistry experiments, and this is not, you'll probably see this in the homework or somewhere else with more sig figs. but let's just write it as 96,500 joules per volt mole. Okay. Now we know that our delta G should end up in joules. So in this Faraday's constant, we have units of energy. Cell potential will be in volts. Okay, that matches that. So N is moles, as you would expect, but it's actually, since it's an electrochemistry, moles of electrons transferred. Okay, remember these are redox reactions. So one species in solution is going to be losing electrons, something else is going to be gaining of those electrons. Well, how many moles of electrons were transferred from one species in the reaction to something else, right? And so you do need to know the balanced equation to be able to see how many moles of electrons in effect moved from the species that was oxidized to the species that was reduced. All right, so keep this equation in mind. This is just going to be a quick video introducing you to a lot of equations and making sure we understand the sign convention and how all of this goes together, and then we'll just crank out a whole bunch of calculations in class. All right, so now let's come up with new equations using what we have. And let me highlight the equations that we have so far. Okay. Let's start with the equation that I just put in the blue box, relating our non-standard delta G to our standard state delta G. And then let's take these two representations of delta G and the cell potential. All right. And I think you can probably see where we're going to go here. We're going to plug in. So we're going to plug in minus NF E cell for delta G, and the same thing for the standard delta G. Let's see what we get. Okay, I'm going to try to keep these all on the screen at least for now. So I'm going to plug in. So this is the non-standard one first. So we have minus NF E cell. Not non-standard conditions. And then we have the same thing for standard conditions. Only difference, of course, is then we would have the standard cell potential. All right. That looks pretty cool, but we're not done. Let's divide through by a negative NF. Okay, and when we do that, we get a nice new equation. Relating the standard cell potential to the non-standard. That's pretty cool, because that's like at the top equation. I'll scroll back up in just a minute, relating our non-standard delta G and our standard state delta G. All right, oops, sorry about that. I do not want to do that, hit the keyboard. All right, so let's box this equation. We will use this equation in class. These cell potential that's easy for us to calculate, and we've already done that, is the standard cell potential using standard reduction potentials. But again, that's somewhat limiting, right? Even if we start the electrochemical cell under standard conditions, okay, as it runs, our concentrations, our pressures of gases, if they're present, will change, and then our cell potential that is non-standard will change over time, and we can actually calculate that. All right. One more thing we're going to do with this equation, just to simplify it a bit, okay, we're going to plug in, and I want you to do this on your own. I'm not going to actually calculate it, but temperature of 298, R 8.314 joules per mole Kelvin. All right. Faraday's constant, Okay, and note that Faraday's constant does have joules in it. That's why we have to use the gas constant with unit of joules. Okay, so we plug in R, we plug in T. Okay, because a lot of reactions will run at roughly room temperature, 25 Celsius. Let's pre-plug R, T, and F already in there. Try this, and you should end up with okay, and that is a natural log there at the end. Okay, so same equation, just the one on the right, a little bit simplified because we're going to say, well, yeah, we'll probably use that one more often than the other one on the left because a lot of our reactions will be at 25 Celsius and we've kind of already pre-solved part of it. That's kind of nice. This is one of my favorite equations just because of the name of the scientist that developed this equation. And that scientist's name was Nernst. And you kind of know how my brain is. For some reason, I think Nernst is kind of funny. I always say it like that, like it's, I don't know. Oh, well, you can go Dr. C, you're silly, which I am. But anyway, that's the Nernst equation. Write that down, kind of know where it comes from. And again, what it does is it allows us to calculate the cell potential at non-standard conditions. All right, just kind of like, and I said I was going to scroll back up, and I actually now remembered, just like we are able to calculate the non-standard delta G from the one that's easier to calculate from tabulated data, the standard conditions delta G. Okay. All right, and the last thing, let's see where we're going to go. What equations are we going to go to? Oh, let's go back up to the top. So there's our standard state delta G, or standard conditions delta G, and its relation to the equilibrium constant. Okay. Well, we can do the same thing with that one. We can take the cell potential, plug that in, see what we come up with. So let's do that. I'll rewrite the equations down here toward the bottom so we don't have to keep scrolling back and forth. All right, now plug in. We end up with minus NF standard cell is equal to negative RT ln K. Let's divide by negative NF again. And let's look at what we get. We get the standard cell potential and its relationship to the equilibrium constant. Wow, that's nice. Okay, so just like the standard free energy change, delta G naught, our standard cell potential tells us equilibrium position. When this electrochemical cell reaches equilibrium, will the equilibrium lie very far to the right or will it lie far to the left? It's really the non-standard cell potential that tells us spontaneity. Okay, and then a lot of times they more or less go together. All right, just as we did up here, as I circle up higher on the page, we can plug in temperature of 298, the gas constant and Faraday's constant. Again, try this on your own just to make sure you know where this comes from. If we plug in RT, again, temperature 298 Kelvin, Faraday's constant, we end up with a simplified version of the equation at 25 Celsius. All right, man, lots of equations. So let's see what we now have. and there's a lot of things written on here. But we did talk about how, when we started, how delta G and the equilibrium constant go together. All right, let's now talk, and I should have done this earlier, looking at our sign convention here. And let's see if I can get some room so I can see where my cursor is. Oh, I can't do that. Okay. We might have to do this down below. Okay, let's go back to these equations and just look at our sign convention. Okay, so delta, let's see, how do I want to do this? Come on, Dr. C. Okay, so if we have a negative delta G, okay, our cell potential, because of this negative sign, will come out to be positive. Okay, and both of those indicate products favored at equilibrium. Okay, positive delta G, negative cell potential, reactants favored. I'm having a tough time here today, guys. I'm really sorry. I just hit the keyboard again. Okay, and we could do the same thing with our non-standard delta G, but that's going to tell us spontaneity. Okay, so for this one, we would have the same thing. Negative, we'll go with positive, spontaneous, forward. Okay, positive delta G, negative cell potential, spontaneous in the reverse direction. All right, so those go together. And then for the last thing for this video, and then I'm going to show you one slide, hopefully, from the notes. Now we have a relation between the cell potential and the equilibrium constant, the standard cell potential. Okay, and remember, it's really the standard one that tells us equilibrium position, and it's going to be as you would expect, positive cell potential. That tells us that products are favored. We should get a large K. All right, so when we do calculations in class, keep that in mind, that if we have a spontaneous, we'll call it a spontaneous electrochemical cell, but spontaneous cell potential, we should have mostly products at equilibrium. We should end up with a large equilibrium constant. If we have a negative standard cell potential, that tells us reactants are favored, and we should end up with small k. All right. Well, I wish I had done a little bit better job. I just wanted to introduce you to quite a few equations here. The nice thing is that they all go together. The free energy change, the cell potential, and the equilibrium constant are all really telling us the same thing in effect. Okay, they're different things. The free energy change is not the cell potential, which is not the equilibrium constant, but they're really telling us where is that equilibrium position. And this is where I'll wrap for today. And again, this is focusing on the standard cell potential and the standard delta G. These are the ones that relate to the equilibrium constant. And here are all the equations that we looked at. Okay, delta G minus NF E cell, delta G minus RT ln K. We did that last chapter. And then here's our relation between the cell potential and the equilibrium constant. Make sure you know the sign conventions, because, or the sign conventions and magnitude, because let's just do one more. If we have a system where products are favored at equilibrium, okay, and we wanted to look at, well, what are our signs for delta G, cell potential, and what is the magnitude of our equilibrium constant? Okay, we've already gone through this, but negative delta G, we kind of started off saying at the start of the semester and just said, oh, delta G negative spontaneous. Well, that's really this non-standard delta G. The standard delta G really tells us equilibrium position. Products are favored at equilibrium with a negative delta G standard. Equivalently, a positive cell potential. Products favored at equilibrium, large K. All right, I think that's enough. Yeah, and I already derived the Nernst equation, and that pretty much gets us through what we need to know for this chapter. We will do calculations in class. We will wrap up by talking about some different types of batteries just for fun. And then we'll move on and do a little nuclear chemistry to wrap the semester. All right, I will see you in class soon. Take care.